So hello, my name is Felipe Romera. Welcome here. We are in the Mobile World Congress at Barcelona, 2025 edition, and we are in the rAppItUp series when we are presenting Ericsson Arabs. We had previously VIB with an exciting presentation on geolocation, and now we'll take over with with cell-shaped Arabs. First of all, I would like to say, what do we mean by cell shapers? Cell shaping is the activity when we can modify the cell footprint in order to meet different trade-offs that we have in our network. These trade-offs are typically coverage, capacity, and quality. So we are developing an intelligent way of achieving optimum trade-off between these three techniques or three KPIs. So I will move to the next slide, where basically we would like to introduce the concept of the cognitive loop. Cognitive loop is the realization that we have in Ericsson of the TM Forum standardization with the different automation levels. So you will see that there are different areas and different colors here. The dark color, or the black one, represents the capabilities that we will have in the SMO in Ericsson Intelligent Controller. So we start by the number one. The platform will give us the measurement capacity. This platform will interact with the network, typically ENM system, and will be able to collect data for us. This data will be typically configuration management, performance management, and also PM events that we can later use. Then this information is served through the Arabs via R1 interface. And this is when we start the orange color that notes the Arab scope of work, right? So we'll start with different areas. The first of all is to understand what needs to be fixed in the network. It's what we call assurance. So we have a set of Arabs that can tell you what cells are not working well and which cells are working fine. What problems do you have, and even to make a classification. Not only that, you can even find a root cause analysis for them. So that will be the first step. Know which cells are not working properly and what needs to be done. The next step, and this is what we'll be focusing the presentation today, is the proposed scenario, right? In this case, we want to say, okay, these are my problems, and how can I fix them? So the Arab will generate a proposal to fix those issues. These issues will be later on moved to the point number 5, the platform, which is the actuation. So Arab will communicate again with the platform via R1 interface so that the changes can be automatically uploaded in the network. You will see that I have not mentioned the point number 4, which is something that we are currently developing. It's the evaluate, right? And it's a shared responsibility between the Arab and the platform. Here, the idea would be the implementation of different intents so that we understand, in case that we have different optimization activities that are proposing changes, which one of them needs to be prioritized over the other or even orchestrated so that we can fulfill an intent that we are setting as users. Okay? So that is the framework or with these Arabs lay. These Arabs, as I mentioned, we have Red Cell Shaper and AES Cell Shaper. Both of them focusing on the cell shaping activities, being read more on the vertical domain for remote electrical tilt, typically for passive antennas. Meanwhile, AES will be more for advanced antenna systems, where we are not only changing the digital tilt, but also the horizontal domain in the SSB. Okay? So I will move to the next one, and here we have a view of both Arabs, right? So here the idea is that the solution is able to detect the shape to the traffic that we are serving in the area. So it can be done automatically, but this is not a trivial process, right? This is a process that requires to understand what are your neighbors and what traffic your neighbors are serving. It's not a simple overshooting detector and tilting, or a simple up tilt of undershooting. Okay? So this is very important, right? As you can see, we have default cell shapes that we can improve. So we can increase the coverage in one and reduce in other, but the coverage will be always kept and the traffic will be balanced in the most efficient way to maximize, as I said before, the trade-off between coverage, capacity, and quality. Okay? There are two domains or two different weapons that we can use to do that. One is the vertical domain in the red for the passive antenna or digital tilt for the active antennas. And also in the active antennas, we have the horizontal SSB shape, so horizontal domain optimization. Benefits, you can see at the right, we can improve our coverage significantly, right? By knowing which is the coverage and the capacity layer and playing with the coverage that we have in each one of them. On top of that, we can also mitigate the interference in a great way because we'll be able to detect where we will have more traffic and when can we offload traffic in both intra-frequency or inter-frequency domains. And then, of course, load balancing, right? Because it's possible to understand which layer is more congested than the other and make an intelligent push to the other. An example of this could be moving traffic from the 4G layer to the 5G if we want to maximize the return of investment in the 5G layer. You can see here some proof points that we have obtained with these rApps, and typically on customer performance improvement, throughput improvement, congestion reduction, and one here that is not shown, but we recently had a delivery to a customer in US when we achieved 75% operational efficiency reduction. This was compared against the way that the customer typically handles the cell shaping activities versus the way we can handle in the rApp world. So the result was that we can be 75% more efficient compared to that. If I want you to remember anything here, is the complexity. This is very complex, right? And whenever we are adding more layers, more technologies, the human being has a limit on the calculations that can be done. And this is what I want to show in this representation. So if we imagine a typical situation, we may have a scenario when we have 4 carriers for LTE, and maybe we have 4 carriers for NR. Let's assume that these carriers in NR are having an advanced antenna system, meaning that I would be able not only to change the digital tilt, but also the horizontal SSB, right, with different shapes. So for the red, we'll have 12 possible options, right? If we assume that we have 8 cells with 3 sectors, 4 of them will be red with 3 is 12, right? If we move to the AES domain, we need to add also the different shapes that you can add, right? On top of that. So if we assume that we could have up to 8 shapes per cell, we end up in 96 options. So this is already quite complex, but what happens if I want to optimize a cluster at cell level? So let's take that I have a 500 site clusters, which is not a very big cluster, right? We can target bigger areas, but this is one small. So if you check the possibilities only for the NR layer, you will end up of having probably 12,000 cells for 4G and 5G. So if we only consider the 5G one, that will be around 6,000. So if you consider only the NR, you will have 96 combinations to the power of the different cells, which is a huge number of possibilities, huge number of calculations that the human being is limited, right? It cannot be delivered by the human being. What is typically delivered today is that these 500 sites, few of them are optimized. Maybe you optimize less than 5%. And the typical optimization that is doing is overshooting detection or undershooting detection. Here we are talking something else. We are talking how to balance the traffic in an efficient way. We are proposing a change for every cell. And this is the complexity that I would like you to remember and understand. Complexity that we are addressing here. Then we talk a little bit about how are we doing that, right? And this is a reflection of our story working on this, because it's not something that we started yesterday. We've been working in Ericsson with the red optimization for several years. We started with the SOM some time ago when we started with what we call an expert system. An expert system is a system that is based on rules typically and defined by senior engineers that they know very well the RF environment. They can find the best rules to be applied, and therefore they somehow transfer their knowledge to these rules. The problem with this is that these rules, first of all, are very costly to maintain, because as technology evolves, you need this person to update them, and therefore they can guarantee performance from day one, but they will not evolve. Here, our approach is reinforcement learning. We are introducing AI here. So this is a change, right? Because we don't need to maintain those rules. We can let the AI to learn from the network. And this is the concept of the reinforcement learning, right? So initially, we know that when reinforcement learning systems are starting, they need to be trained before with a lot of data. And to do that, we have a simulator where we can simulate in a very efficient way the different RAN configurations, different city morphologies, different antenna types, different building types, so that we run a lot of iterations in an offline mode. Therefore, we get our pre-trained model available for production. And here, when it is already good enough, it will be the point that we decide to make it ready for production. So whenever we deploy that into the field, the algorithm just will start learning and learning and learning. And therefore, it will be outperforming the expert system as the time progresses. Okay? So how does it work? It works with this model, right? This reinforcement model that is based on the network and an agent. Network will provide an state which is defined by the configuration and topology and the KPIs. These KPIs are based on PM events data that we process, and we typically call them synthetic KPIs. Then this state is fed into the model, our AI model that we have trained already. So this model will propose a change, okay? And this change will be implemented automatically in the network. So this works typically in a daily iteration. So every day we will load a different change, okay? So once we have loaded the change, we will see the feedback sent to the model again. This feedback will tell the model, okay, was my changes going in the right direction? Were improving the optimization strategy that I wanted? If that is the case, these changes will be reinforced and will be, in the other case, these changes will be penalized, will not be encouraging those changes, okay? So this is a continuous cycle that we call iterative and typically lasts from 6 to 8 iterations. So after 6 to 8 days, the model will have learned everything, right? And will be ready to work independently, okay? And what do we do in every iteration? We can up till, we can down till, we can keep the till the same, or we can change a different SSB shape in the horizontal domain for the AES, right? We are using for the AES a feature in Ericsson called flexible cell shapes that is composed of 12 different shapes, some of them being super narrow, some of them being super wide, so that we can select the more effective for each one of them. I will move to the next one. And basically, just to conclude this presentation, we would like to reflect a little bit on the business values that we see in this area, right? We have some color coding here, right? The blue will be basically for OpEx efficiency, that in this case we have with revenue boost. Operational efficiency means that we will be able to do more with less. We can deliver more activities, more sites with less manpower. And revenue boost will be related to performance improvement that we can obtain in the network. So first of all, reinforcement learning is very important. We see as a foundation or a pillar for this. The reason is that it will automatically adapt to the traffic that you have in your network, right? Once it has learned the network, if you have a traffic change, it will be automatically able to detect and react upon. So this is very powerful, right? Then we can do simultaneous optimization in the vertical and horizontal domain. So this is the reflection of the complexity that I said before. We have so many options that human beings just cannot do that. You need AI. And if you want to do at cell level, you need to go for simultaneous optimization that is here. So again, a great operational efficiency reduction. And of course, multi-technology awareness. Here, our remote electrical till optimizer, right, can work with 4G and 5G at the same time. So in the case that you have shared antennas between 4G and 5G, you will need to make a decision of the driving technology. We can do that here, and therefore we can maximize the performance. If we move to the right, then again, we have increased operational efficiency as a target, and also transformation agility. What do we mean by that? By transformation agility, we want to reflect on how the operator, the CSP, can move to a new way of working that is more aligned with the cloud native and the CI/CD, right? And so we want to move in that direction. And to do that, we have the AI explainability. So we will include in these applications a way for the user to understand how the AI decisions are taken and why are they, right? So this will help us on the transformation agility. And of course, we recognize that the AI is very powerful, but sometimes we need to put limits to that. And that is what we call safety shields. So in the safety shields, we'll be able to adapt the policy that the operator wants to that, so that we can limit the AI if that is a requirement. We are aware that many operators have different policies, and we can comply to them with this. And then, of course, we can reduce the the capex as well, because this optimization has proven to increase the spectral efficiency, right? And we know that the more bits we can accommodate per hertz, the more efficient we are, and the delayed hardware expansion. So this is linked to that. And finally, very important, the quality input data. You need to have the right data in order to make the right decisions. And you only do that by taking the data that really matters. In this case, the data that really matters would be the PM events that are coming from the users, right? We need information from the end subscribers. So this is very important. On top of that, we don't require predictions. Typically, when you have predictions, you need to have very fine-tuned predictions to do this in an accurate way. Therefore, you will need to do a lot of drive tests. Again, this is helping on the sustainability. And I will wrap it up by a summary. So what are we doing? We are doing cell-shaping optimization for 4G and 5G. In the 5G, we can also play in the active antenna system with the SSB width, right? We have different AI models that cater for the trade-off between coverage, capacity, and quality that the user can steer. And we can consider the traffic shift between different technologies, 4G and 5G. How are we doing? So we have the AI model based on deep learning with a pre-trained model that we have in a simulator like this that you can see. And then we can train with different city types, different antenna types, different antenna heights. And of course, it will provide incremental adjustment every iteration. And the agent will always continue to learn. And also very important, API is provided, right, in case it's important. Input data, as I said, focus on end user experience. So we need configuration management and PM events coming from the users. And the output, as mentioned, digital tilt changes, horizontal changes in the shape, and we can have a daily evaluation and resolution. And that would be the end of my presentation. So thank you very much for listening.